certain marks, then only you can join any college to continue his studies. So if a student wants to join college, he should have cleared his plus two exam. So that is called enabling. In the same way, if you want to what the transition to act, if you want the transition to fire, it should be enabled first. What is that enabling? A transition tree is said to be enabled if each input place P of T contains at least the number of tokens equal to the weight of the directed arc connecting P to T for any P in T. If you see this graph, uh, on the arc, each and every arc, I have put a number. On the first arc, I have put number 2. The second arc, I have put number 1. And again in the output arcs, I have put number 1. What is this? This is the weightage of the arc. That means, if in this example, if you want to fit a bicycle, you need minimum two wheels and a frame. Then only that operation will be carried on. Otherwise, that will not happen. If the number of wheels is less than two, you cannot fire this transition. So if you want to fire a transition, the number of tokens should be equal to the weight of the directed arc connecting P to T. So if you want this transition to fire, your wheel place should have at least two tokens. So that which is equal to the weight of the directed arc. The two denotes the weight of the directed arc. So this place should have at least two tokens for this transition to fire. At the same time, similarly, you need at least one frame here in this place for this transition to fire, and these two things should happen simultaneously. That is another condition. When this condition holds good, only this transition will fire. So this is called enabling rule. So if we want a transition to be enabled, each input place P of T should contain at least the number of tokens equal to the weight of the directed arcs connecting P to T. This is enabling rule. Once the transition is enabled, it will be ready to fire. That is, it will be ready to process whatever is required from that transition. So firing rule governs the flow of tokens. Only enabled transition can fire. The firing of an enabled transition T removes from each input place P the number of tokens equal to the weight of the directed arc connecting P to T. It also deposits in each output place P the number of tokens equal to the weight of the directed arc connecting T to P. Let me explain this concept. What it says is, I said if you want the transition to fire, it should be enabled. Enabling rule is given. Okay, what happens when it fires? When it enables, it fires, what happens? If it fires, it will take the number of, that is two, here in this example, it will take two tokens from wheels place and one token from frames place, and it to the cycle place, it will deposit one token. That is what happening in when you fire. So the firing of an enabled transition removes from each input place. From each input place, it will remove the number of tokens equal to the weight of the directed arc connecting P to T. The same way, it will deposit in each output place P the number of tokens equal to the weight of the directed arc connecting to P. This is what happens when a transition fires. To make it more clear, I have taken a small example just to show you what is this firing does. I have taken a small fire alarm system as an example. This fire alarm system alerts when high temperature and smoke is detected simultaneously. So I have modeled this using Petrinet. So if you see this Petrinet model before firing, I have used three places. First place says smoke, second place says high temperature. If there is a token inside the smoke place, and if there is a token inside this high temperature place, it says that smoke and high temperature is there. There is high temperature in smoke. So at that condition, the alarm should be triggered. So if these two tokens are present in this place, this transition trigger will fire. So what happens when it fires? When it fires, the alarm will be on. After firing, you can see that these two tokens are consumed and a token is deposited in the output place. So before firing, there was no alarm. Once these two things are smelled, automatically the alarm is triggered. Now, after firing, alarm is triggered, alarm is on. So this is a small example of a fire alarm system which we made use of Petrinets. When you see this before firing, when you see the arcs, nothing is written on the arc, so it shows that only one. So one token is enough for this arc, and similarly in high temperature, the arc between high temperature and trigger, I have not written anything, so it shows that number one. So only one token is enough on both cases to trigger this alarm. So after firing, it has consumed both the tokens and it has deposited one token which shows that alarm system is on. So this is a small example of a fire alarm system. Uh, Next is what sort of systems can be modeled using Petinet? That is our question. I have shown some examples. I'm telling you that these and all can be modeled, places, transition, all those things and all. But what are the conditions? What sort of systems can be modeled using Petinet is our next question. So systems that exhibits the following characteristics. That is, any system which has concurrency, any system needs decision making, or any system which runs synchronizingly, or any system which has got priority. All these systems can be modeled using our Petrinet. Uh, I have given you a small example again how to model a sequential systems. You have taken sequential execution. I hope we all know that sequential execution is something which happens one after the other. Nothing will happen simultaneously. Things will happen one after the other. Example for sequential system is in our teaching line. If you want to conduct test, we will go for a monthly test, and then we'll go for a quarterly exam, then we'll go for a half-yearly exam, then we'll go for annual exam, which happens sequentially. That sort of things, that sort of systems can be modeled using Petrinets. Conflict can be modeled. So what is conflict? If you have a single scanner in your office, but you have too many things to scan, there comes a conflict. Which one has to be scanned first, and what basis it can be scanned? So there is only one scanner, but two jobs have to be done. So that sort of conflict situations also can be modeled. That is what I have done. I have shown a Petinet model. There is a place with a token, but this you have only one token, so only one transition can fire. Either T1 can fire or T2 can fire. So there is a conflict over there. That sort of systems also can be modeled using Petrinets. The other one is concurrency. Concurrency is two things happening simultaneously in a college system. If the college is running, that means classes will happen. That is, different classes will happen simultaneously, concurrently. There is an example for concurrency. All first year classes, second year classes, third year classes will happen concurrently at the same time. Such sort of systems which shows concurrency, that sort of systems also can be modeled using Petrinets. Synchronization. Synchronization, we can take up the same example of this bicycle assembly line. That is synchronization in the sense you need two raw materials to make one new things. Like we have wheel, we have frame, and we put wheel and frame together to make bicycle. But before that wheel has to be produced, the frame has to be produced. That comes from different line. Once these two things are ready, and this transition T1 fires to make another product. So synchronization can be modeled using Petrinets. The other one is mutually exclusive events. Mutually exclusive events is if certain event happens, which will stop the other event. Again, going back to the same bicycle assembly line. If the bicycle assembly line assembles tricycles also, let us take it as an example. There is an assembly line which assembles bicycles and tricycles, but it can do only one job at a time. So, if the assembly line is taken for assembling bicycles, this tricycle assembly will be stopped. So, that situation is called a mutually exclusive situation that can be modeled using our Petrinets. So, here there is only one token, but so many transitions to be fired. So, using the token in T1, T1 can be fired and T3 can also be fired. If T1 is fired, T3 cannot be fired. Or if T3 is fired, T1 cannot be fired. So this is a mutually exclusive case. These cases also can be uh, modeled using Petrinets. Okay, we know what is Petrinet, what is definition of a Petrinet, how to model Petrinets, and what sort of systems can be used can be used. What sort of systems can be modeled using Petrinets? We have learned all these things. Okay, after modeling, after using Petrinets, what are we going to do with this model? I have created a model, I have created a graph, and I'm showing all sort of things. But what are we going to do with this model? So that is the next case. We have some properties of Petrinets which can be used to analyze and study the behavior of the model that we are creating. So there are two important properties of Petrinets. One is behavioral property, the other one is structural property. Behavioral property depends on the initial state or marking of a Petrinet. That is, based on the marking of the Petrinets or initial state, you can identify behavioral properties. Structural property, as the name suggests, structural property depends upon the structure of a Petrinet, the topology of the Petrinet. So these are the two properties that we have in Petrinet model. I have given you a set of behavioral properties here. One is reachability, that one is safeness, liveness, deadlock freedom. What is this reachability? Reachability is when you start up with something, you are doing some modeling or you're studying something, uh, that there will be a end state. You want to see some results over there through some stages. You start with one stage, after doing some experiment, changing the parameters, you will come to a end stage. So reachability says refers to that ability to reach a particular marking state from the initial marking by firing transitions. That is called reachability. What is that? In the fire alarm system, the initial stage was just identification of smoke and high temperature. The final stage after firing, the final stage was the alarm was on. That is the last stage. So I have taken a small example where I have only two stages, but there are things where you have n number of stages. So it has to cross all the stages by firing all the transitions under certain conditions. So while doing it, you have to check whether is it possible to start from initial state and reach the desired stage. So you have to study that. So this reachability analysis helps us to study whether so the stage is attained or not. Next is safeness. When you do some experiments, some undesirable conditions will be there. You can identify that undesirable conditions and eliminate that thing using the safeness property. By studying safeness property, this will ensure that certain undesirable conditions never occur in the system. If it happens, it will alert you so that we can avoid such conditions so that our system will be safe. That is our safeness property. Liveness property. The liveness refers to the ability of a system to eventually reach a desired state despite ongoing activity. That is, without any interruption. Is the system working on? Is the model working on? Is the system working properly without any deadlock, any problem? Is it working? So using this liveness property, we can check whether the system is doing good or not. The other property is deadlock freedom. Deadlock is you cannot see any progress in the system. If there is any problem in the system, you cannot see any progress over there. A small example is if you don't have any proper raw materials, then the system will not work. So that can be checked using this deadlock freedom property. Petrinets can be analyzed to ensure that deadlock situations cannot occur, ensuring continuous operation of the model system. So using this property, you can check is there any hindrance, will there be any deadlock, if at all it happens, how to overcome it. All these things can be studied using deadlock property, deadlock freedom property. Next is boundedness property. Boundedness property is to check whether the number of tokens in each phase of the pertinent remains within certain bounds. That is to check the upper limit and lower limit of the system. Uh, Again, in this bicycle manufacturing unit, you bring in raw materials to prepare all the parts and you will store it in a place. And after manufacturing, cycle is the output. Again, you have to store it in a place. But there is a condition that you cannot bring in n number of raw materials or you cannot store n number of cycles. So you need to have, you should know what is the boundary, how many cycles you can store, what are the, how much raw materials you can store. You cannot exceed the limits. So that is an important thing that has to be noted. So this boundedness will check that this boundedness property will tell us that what is the boundary for the system. Is it bounded or unbounded? If it is unbounded, what happens? So this boundedness property helps us to prevent unbounded growth. Fairness property ensures that all parts of the system have an opportunity to execute and progress over time. In a system, if you have two or three lines, all the lines, all the subsystems should work together. It is not that if, we all know if it is a very big system, we will have many subsystems. So, in the system to work properly, all the subsystems should work properly. If you have any problem in subsystem, the complete system will get disturbed. So, this fairness property ensures that all parts of the system have an opportunity to execute and progress over time. Fairness considerations are crucial in distributed systems and concurrent execution environments to prevent starvation and ensure equitable access of resources. That is, using this property, we can check whether the resources are used properly or equally. Is there any starvation and any subsistence? All these things can be checked using fairness property. And concurrency, as I told you, Petinet helps us to model concurrent systems also. Here, concurrency allows multiple transitions to occur simultaneously. That is, if we have many transitions simultaneously, all the transitions can fire if it is enabled, if it has a proper input. So that can be checked using this concurrency property. The next, I told you we have two properties. One is behavioral property, the other one is structural property. We have discussed behavioral property. The next is structural property. Structural property gives us the insights into the structural organization and properties of the model system. Some important structural properties are degree of place transition, invariance, conflict resolution, and symmetry. These are the properties that we check in our constructed models. And how do you construct a model? After constructing the model, you will try to analyze the model. So that is very much done in this Petinet modeling. We do this using three approaches. We have three approaches here to analyze the constructed model. One is reachability analysis, the other one is matrix equation approach, and the third one is simulation. This reachability analysis involves the list of all reachable markings, but the pros, when you talk about pros and cons of this reachability analysis, sometimes it suffers from space explosion. State space explosion means in some of the places many tokens will be there. There is too much of activity will happen, too much of outcomes will be there. So when you do this reachability analysis, there's a small issue in this space, sorry, state space explosion. The next is matrix equation approach. In matrix equation approach, we create matrices from the Petrinets graphical model itself. We try to create matrices and study the properties. And it is powerful, but in many cases, it is applicable only to special subclasses of Petrinets, special phases. The next is simulation. Simulation is done for a complex Petrinet model. Discrete event simulation is an option to system properties. That is, if you have a complex system, you can use simulation to construct the model. So these three are the analysis that we are using in Petrinets. I have taken a small case here to show you what is this reachability analysis, what is this Petrinet. Uh, this reachability analysis is conducted through construction of reachability tree and reachability graph using an algorithm. That is, after constructing the Petrinet, we will construct reachability tree and reachability graph to study to analyze the given system. My case study is I have taken a simple performance monitoring model. That is, here I am monitoring a CPU. There is usage of CPU levels in a computer. That is my case I've taken. If you see the computer networks, if you go to a computer network center, you can see many computers connected to your server. The server will manage all the computers. So there will be a manager in the server. And in each and every computers, there will be an agent which will monitor the usage of CPU. If there is a over usage of CPU, it will send information to the server, there is the manager, and the manager will give a alert through SMS or WhatsApp message. It will give a alert that the CPU is used more, it's overloaded. So this is the algorithm. This is what I'm doing in this Petinet model. I have used 9 places here to represent different stages of this model, and I've used 8 transitions. Uh, and it is one bounded. I am using only one token here. If a token is there in the initial place, P naught is my initial place here, and P9 is my final place. This is one cycle, that is starting from P0, reaching to the P8 last end. This is one cycle. In this cycle, the CPU will be read. The agent in the system, the computer CPU, it will read the value of the current CPU usage level, and it will send the value to the manager. The manager will read the CPU level, and it will compare it with the threshold level. If the CPU usage level is greater than the threshold level, the manager will send an alert through SMS or WhatsApp messages. This is the small example that I have taken. I have drawn the Petinet for this, and I have drawn reachability tree and reachability graph. If you see the reachability tree, keenly see it is nothing but it is made up of markings. To start with, I have M naught. M naught says 10101010. This is nothing but the number of tokens in the places. I said I have used 9 places, so I have written 9 the 0 1 values over there. So 1 denotes there is one token in place 1. 0 denotes there is 0 token in place 2. Again, third one denotes there is one token in place 3. So this is the initial marking. When the first transition fires, the token the system changes. The token will move from one place to another. That is represented in marking 1. And the next transition fires, the other marking will be there. So this is drawn as a reachability tree, and from this reachability tree, I have drawn reachability graph. The reachability graph shows that there is no deadlock. The system, the cycle is working fine. Starting from M1, it goes to M2, M3. The cycle is going fine. And after certain, I have given a small break. That is, from one checking to other checking, I have given a small interval. That is, first checking will happen the first minute. After 10 minutes, again it will check the second round. So I have given a small space. So this graph shows that there is no any problem in this system. This is going for fine, and it is bounded, and it is one bounded because only one token is there, and it is live, and there is no dead transition. So this is the just for an example, I have taken as this CPU monitoring form, and I've created reachability tree and reachability graph. From this analysis, I have made a conclusion that the reachability set is finite, and the number of tokens of every place in all marking is bounded. There is no dead transition. All transitions are working fine, and I have concluded the net is bounded. If it becomes unbounded, you cannot control the system. It is bounded, so everything is working fine. So this is the conclusion I got from this small example. So simulation, we are talking about this Petinet simulation, which is a convenient and straightforward yet effective approach for engineers to validate the desired properties of a discrete linear system. And there are some advantages. It allows one to derive the temporal performance for a system under very realistic assumptions. That is, you can using this Petinet simulation, you can change your parameters then and there and check the outcome. Uh, that is the temporal performance for a system. And I was talking about Petrinets, but there are many extensions of Petrinets. I was talking about transitions. So if you add timings in the transition, that is, if you say that delay the firing for some time, if you try to add timings to the transition, the Petrinet turns into a timed Petrinet. If the time you add is deterministic time, we call it as deterministic time Petrinet. And if you want to add probability to the transition firing, so we can associate it with an exponential distribution random delay. And such petrinets we call it as stochastic petrinet. A petinet which has all these three things, that is immediate firing, deterministic firing, and stochastic transitions, we call it as generalized stochastic petinets. And very important extension of pettiness is hierarchical pettiness. This hierarchical pettiness allows decomposition of a given complex model in more manageable subnets without affecting the model property. That is, so it shows that you can model any big system using Petinet, using hierarchical Petinet. You can divide it into small subdivisions and model it, and finally you can assemble it to get the final outcome. That is an advantage of Petinet. And if you want to have simulation tools along with its features, this link will help you. If you go use this link, you will get a list of Petinet simulation tools along with the features descriptions. It is there in Petinet World website. Application areas of Petrinets, especially it has been used in computer science department, computer networks. As I told you, it is used in manufacturing plants, command and control system, logistic networks, and run flow. And these are a few important examples that I have given to you. And application areas where I have used Petrinets. I have done models using Petrinets. One is monitoring complex systems. I have modeled the complex systems, and I have studied the behavior. And I have modeled tsunami warning system using Petrinet, and I have studied its behavior. And I have modeled IT infrastructure components. I have done dynamic alert management. All these things I have modeled, and I have applied all the properties, and I have studied the behavior of the system under certain conditions. I hope this presentation would have given an overview of Petrinets and what can we do using Petrinets and what is Petrinet. Uh, if you have any doubts, feel free to ask.
Thank you, ma'am. Thank you, ma'am, for your nice presentation, ma'am.
Thank you, ma'am. Is there any questions? I'm ready to. answer the questions, ma'am.
Participants, will you have any queries? Kindly unmute your audio and ask.
I would like to ask a question. For how many of you this Petinet is new, ma'am? Is it new for everyone, or have anyone have heard about Petinets before?
Audible? Hello, ma'am.
Yes, ma'am.
Ma'am, Ammu ma'am.
Yes, ma'am. Yes, yes, sir.
Uh,
Yes, sir.
Hello, sir.
Hello,
Can you
ma'am.
hear
I'm
me?
audible, ma'am.
Yes, yes, I can hear you, people.
Sudha ma'am, you can proceed, ma'am.
Ma'am, thank you for your
Yeah,
session.
good
It's a
afternoon.
wonderful
Sir, I
session.
have one doubt, sir. Please give a
Yes,
time
yes,
for me.
please, please, ma'am, please, ma'am.
All your
Yeah,
points are
very good
valuable
evening,
points.
ma'am. This
We
Balaji.
is,
are mostly benefited, ma'am. Thank you, ma'am. Thank you very much, ma'am.
Thank you, sir. Thank you. Sudha, ma'am, you can ask your question.
yeah, good evening, ma'am.
Good evening.
Your presentation is very nice. It's a very trending subject. But nowadays, I don't know how many of them using that. But I'm very impressed in this topic, ma'am. Only one question I have it, ma'am. While going for a case study, what are the complications we can face, ma'am, while using Petrinets?
Ma'am, complication is, ma'am, you have to choose a right Petinet model, ma'am. As I
Okay,
told you,
ma'am.
if you
Hmm.
model a complex system, you should not go with a simple Petinet model. You should go for a hierarchical Petinet model. So if you
Okay,
choose the
ma'am.
correct model, you will not face any complication because the properties are very strong. When you use the properties, it will tell you where you find where you are lacking, what sort of deadlocks are you are facing, where to how to solve it. All those things are there in the properties, and the important thing is we can visualize it what is happening. If you have a deadlock, you can visualize the graph because the movement of tokens. We have a software for this. From using that software, if you model the things, you can visualize what is happening inside the system by the movement of tokens. So if your token gets stuck somewhere, so you can identify there is a problem. So you can identify what sort of problem is there. Is there any unavailability of things, or is there any unboundedness? Or, so you can easily identify the problems and you can rectify it. So
Okay, ma'am. Okay, okay.
thank you so
Thank you
much,
so much, ma'am.
Sudha,
It's
ma'am. Thank
very
you.
nice presentation. Application part also you have explained. So it is a very useful, ma'am. But the Petrinet is very new to me. So I am
Yes,
very impressed in your presentation, ma'am.
that is
Thanks a
what.
lot, ma'am. Thank you
Thank
so
you,
much.
sir. Thank you, Sudha. I chose the subject so that if anybody is interested in doing a PhD, they can select this particular topic because it's a very interesting topic and emerging topic, emerging subject. That's why I took this topic. Anyway, thank you 100% here for your patience, and thank you all, thank you management, principal, and staff members for giving me this opportunity. I'm waiting forward, looking forward to do more things like this, ma'am. Sujata, ma'am, thank you very much for your invitation.
Thank you, ma'am.
Thank you, ma'am. Can I leave the session?
Ma'am, you can wait for the photo session, ma'am.
Yeah, sure, ma'am.
So now you request every participant to turn on your video for the photo session. Thank you, ma'am. Thank you for your nice presentation, ma'am. Thank you, ma'am. Thank you, ma'am. Now I request Mrs. D. Flora Evangel, one of the coordinator for this FTP, to deliver the vote of thanks.
Good afternoon to one and all. It's my immense pleasure to give vote of thanks on this wonderful occasion. First of all, I would like to thank the Lord Almighty for his presence in leading this session in a successful manner. My intent stands to our founding father, Reverend Father Dr. K.E. Arulraj, for his guidance, and my heartfelt thanks to our immediate administrator, Reverend Lady K, for her continuous support and encouragement. And also my sincere thanks to our principal, Dr. R. Mohamad, for his guidance in conducting this meeting.
Sujata ma'am, is it over?
My profound thanks to our resource person, Dr. Ammu Qudsiya, HOD, for her excellent motivational speech
Ma'am.
on the topic modeling and stimulation on Petrinets. I would like to thank all the participants from various institutions who actively participated in this program. I would like to thank our technical team for their continuous support in making this program a grand success. Thank you, one and all.
So thank you, ma'am. Thank you, ma'am.
Thank you.
Thank you so
Thank you,
much,
ma'am.
ma'am. You can leave, ma'am. Thank you, ma'am.
Thank you. Thank you so much.
So participants, do fill the feedback form which has been posted in the chat box. Thank you all. Meet you all in tomorrow's session. Thank you for your participation. So thank you all.